Hello and welcome to our lecture on coasts. Today we'll be talking about the nature of coasts and the several different processes that occur to shape coasts. So coasts are influenced by both marine and terrestrial or land-based processes. So we have the erosion, which is the removal of sediment, the deposition, which is the placing of sediment that influence coasts. We also have changes in sea level that influence coasts as well. The eustatic change in sea level is a change in sea level that can be observed all over the world ocean. So it's a global change in sea level. Now this is a dramatic influence on sea level, a eustatic change. And several things can cause a eustatic change in sea level. These include glaciation, the volume of the ocean's container changes, and the density of ocean water. We'll talk about glaciation a little bit, but first we mentioned the volume of the ocean's container. That changes. The sea level will change because if the volume of the container becomes smaller, water height increases. If the volume of the basins becomes larger, the water level lowers. And how can the volume of the ocean's container change? Well, that's with plate tectonics. As continents shift, being driven by plate tectonics, the ocean basins take different sizes and shapes, changing their volume and therefore changing sea level. And also the density of ocean water. As the climate changes, say as the climate warms, water in the ocean becomes warmer, and we know that as water becomes warmer, its density decreases, and so it takes up more volume. So the same amount of water takes up a larger volume. So a warmer ocean has a lower density and takes up a larger volume, and thus would result in sea level rise, where a colder ocean would have a larger density, take up less volume, and result in sea level falling. So to go back to glaciation, glaciation probably has the strongest influence on eustatic changes in sea level, and glaciation, the extent of it, is determined by the state of Earth's climate. So as Earth's climate cools, what happens is precipitation that falls in the form of snow, it accumulates on land. And if the climate is cool enough, then not all of the snow that falls during the winter will melt during the summer. And so year after year, you will have a net accumulation of snow. And as this snow accumulates year after year, decade after decade, it accumulates to form what's known as a glacier. Now, where did this water come from that's precipitating as snow and remaining on the continents? It came from the ocean. And so as glaciers grow and become larger and more extensive, that water that's forming those glaciers is coming out of the ocean, so the sea level lowers. And so in periods of geologic time where Earth's climate was cooler and glaciation was more extensive, sea levels are much lower. And so here we could see sea level change in feet from present day. This is present day is 0, so this is feet below present sea level, and this is in meters over here. And on the y-axis, and on the x-axis we see thousands of years ago, with over here being present day. So this is 2, 4, 6, 8,000 years ago. And so we could see as we go back in time, sea levels were much lower. And so this rise in sea level as we go from about 20,000 years ago to present day is called post-glacial sea level rise, because this sea level rise was a response to the end of the last glacial maximum, also known as the Ice Age. Okay, so as the Ice Age phased out and all the water trapped in those glaciers melted It flowed as runoff across the continents into the oceans, causing sea levels to rise. And you can see that sea level change is fairly substantial. We have 400 some feet in sea level change over the last 20,000 years. And just to give you an idea, 10 feet is roughly, or it's approximately, one floor of a commercial building. So 400 some feet would be 400 some stories of a commercial building. So sea level projections, they vary according to models. So these projections are made using climate models that climate scientists make. And basically what factors that sea level projections depend upon is how climate changes in the future. Is it more rapid? Is it slower? And that depends on the amount of greenhouse gases being emitted into the atmosphere. Those greenhouse gases are emitted through the burning of fossil fuels and so forth. So we have this observed change in sea level right here. So here we have time on the x-axis, 1950 on the far left, 2010 on the far right. And this is sea level rise in inches. Okay, so this is present day, 0. So negative numbers is sea levels below present day, and positive numbers is sea level above current day. And you can see some projections that are more conservative put us at a couple inches, maybe around 6 inches of sea level rise by the end of the century, while other other projections that are not so optimistic about our reduction in greenhouse gas emissions can put sea level rise to be around almost 24 inches or 2 feet by the end of the century. And so to show you how drastic this eustatic change in sea level due to glaciation can change coastlines, here we're looking at a map of the southeastern United States about 18,000 years ago at the peak of the last ice age. And you can actually see the ice sheet right here. So all this water trapped in these ice sheets on the continents came from the ocean, therefore we have lower sea levels. So you can see that this is the coastline at that last glacial maximum. So this is obviously Louisiana, Alabama, Florida, Panama, Florida, and then down here up the east coast of the United States. Now, if all the water that is currently trapped in ice as glaciers on land melted, this is what our coastline can look like. This is rising sea levels because that ice trapped in water trapped as ice on land melts and enters the ocean. And so you can see that this will be a big problem moving into the future as large portions of the population live along the coast and will be displaced. So those are global changes in coasts driven by changes in sea level. So now we're going to talk about more regional processes. And so first we're going to start with erosional coasts. So erosional coastlines are those in which the dominant process that is occurring along them is the removal of material, mainly sediment. And about 70% of U.S. coastline is erosional coast. So what makes a coastline erosional coast is the amount of wave energy that it experiences. So if there is a lot of large waves, so this is a lot of large waves hitting the coast, there's going to be a lot of energy to erode sediments, to remove sediments. And so typically coasts that are on, say for mid-latitudes, coasts that are on the eastern edges of ocean basins, say like the Pacific coast of the United States, it's on the western edge of the Pacific, so that the westerly winds, which blow from west to east, they blow across the Pacific towards the west coast of the United States, generating large waves that batter the west coast of the United States. causing it to be a high-energy coastline and therefore mostly erosional coastline. Some features that are commonly associated with erosional coasts are sea cliffs, sea caves, sea stacks, and wave-cut platforms. And we're also going to talk about shoreline straightening, which occurs due to selective erosion. So, erosional coastlines are not only shaped by the erosion of waves, wave erosion. There is also erosion from land that shapes erosional coasts. So you can have stream channels being erosion in stream channels, abrasion of wind-driven grit, the freeze and thaw cycle of water, which causes erosion, plant root probing, so plants growing into cracks of rocks and breaking them apart, glaciation, glaciers can break apart rock and erode them, rainfall, and also finally the dissolution of rock and soil by acids decomposing them, acids, naturally occurring acids, and acid rain from pollution. So these processes occur on land near the coastline that also influence the shape of the coastline. So first, we're going to talk about the formation of two features commonly associated with erosional coasts, and those are wave-cut platforms and sea cliffs. So I'm just trying to get my pen. There's my pen. Sorry about that. So you can see that this is the land, and this dashed line represents the original land surface. This is the original land surface. The waves were crashing right here on this land, slowly eroding the land away and cutting back until it created a notch. So this is the original land right here. It created this notch in here. And in creating this notch, it created this flat surface known as the wave-cut platform. And eventually the rocks overhanging this notch, they broke off and fell into the water, leaving behind a sea cliff. So, leaving behind a sea cliff. And this process continues where the waves erode a notch. So they erode this notch, overlying rock breaks off, and as a result forms a new sea cliff and an even larger wave-cut platform. So here you can see that this has progressed to the point where all of this rock has been removed and this large wave-cut platform has been carved. And right here is the current notch. Well, this rock will eventually break off, causing the sea cliff to move even further back, even further landward. Here you can see this is a picture facing the coastline, I guess facing seaward from the coastline. You can see this flat rock right here. This is the wave-cut platform, and then the sea cliff is the face of this cliff facing the ocean. You can see the wave-cut platform there. Sea stacks and natural arches are also features associated with erosional coastlines. And sea stacks are formed whenever headlands or regions of land are eroded away, but there's some more erosion-resistant rock left behind, and so it's called a sea stack. And if the sea stack gets a hole eroded within it, it'll become a sea arch. And so different coastlines, depending on what type of rock they're composed of, erode at different rates. So coastlines composed of hard rock, such as granite, they will erode slowly, as slow as a few centimeters per decade, while coastlines made of softer rock, more easily eroded rock, such as limestone, they can erode backward as fast as a few meters per year. Here's an example of a sea stack right here. So this rock used to extend out past this sea stack, and all this rock has been eroded away. For some reason, this rock here is more erosion resistant, has been left behind. It will probably be eroded away in the future, but it's still there now as a sea stack. So sea stacks are literally carved out of the land. So here we see a bird's eye view. This is what's called a headland. This is a region of land that sticks out into the ocean, and the insets are known as bays. And what happens is whenever waves come into the coast, the water is shorter near shallower near the headlands, and so these waves enter shallower water here, but are still in deeper water out here. And we know that whenever waves enter shallow water, if the water depth becomes less than half their wavelength, they begin to sense the sea floor, and as the depth decreases, the wave speed decreases. So the wave speed begins to decrease of these waves as they enter shallower water. Meanwhile, the same wave further over here from the bay is in deeper water and it's traveling at a faster speed. It's in deeper water. And this results in the bending of the wave front or the wave line in a process that's known as refraction. And you can see that the refraction causes the waves to bend toward the headland and away from the bays. So this refraction is literally focusing the wave energy on the headland and defocusing it away from the bay. So you're going to have the largest amount of erosion where you have the most wave energy. And since that wave energy is being focused on the headland, we're going to have erosion at the headland. And since that energy is being defocused or focused away from the bays, you're going to have sediment deposition in the bays. And so over time we see that's what happens. The headlands erode back because of the focused erosion, and sediments are deposited in the beach because of the unfocused wave energy. And so you can see these sea stacks are formed by the eroding of this headland, leaving that rock behind. You see how the shoreline is becoming straighter than it was before. So eventually the shoreline would become straight and it would become stable. Now here's an example of an irregular shaped shoreline. We have bays and headlands. Bays and headlands. There's a sea arch. Over time, wave erosion has cut this sea cliff, and this sea island is breaking up the wave energy, so preventing some erosion there. But eventually that island erodes away, and erosion can erode back this headland. We have sediment deposition here, and we have the result is this straightened coastline, reached stability. I already mentioned that land erosion can shape coastlines as well. And so land erosion can exist two major contributors as stream channel erosion and glacial erosion. So for example, the Chesapeake Bay and the Delaware Bay were all river valleys that existed during the last ice age when sea levels were out here. So these are large rivers that ran down through here, and they eroded these large valleys. And as the glaciers melted and sea levels rose, those large river valleys flooded, forming these bays. Similar thing happened with Narragansett Bay. These were river valleys at the peak and during the last ice age, and the ice sheet came down and it carved these valleys wider and deeper. And then as the glaciers melted and sea levels rose, these valleys flooded, forming the Narragansett Bay. Sydney Harbor in Australia was also formed by stream erosion. So the stream eroded a valley wider and deeper during the last ice age, and when the ice age lifted and sea levels rose, those valleys became flooded. Fjords are formed in a similar way by glaciers eroding coastal river valleys wider and deeper, and as sea levels rise, those valleys flood, forming fjords. So the other main type of coastline is a depositional coastline. And this is a coastline in which the dominant process is the addition of sediments, or the deposition of sediments. Around 30% of U.S. coastlines are depositional coastlines. So these coastlines are those that have sediment deposited on them. So here we see a beach with very fine-grained sediments deposited on it. So this is a depositional coastline. And so beaches are a common feature of depositional coastlines. And a beach is a zone of loose particles that cover all or part of a shore. So the sediment at a beach can come from near or far. And sediment is always being transported along the beach. The sediment at a beach varies seasonally. You can see here, these are the picture of the same beach. But during the summer, there's all the sand here, this very fine-grained particles. And during the winter, that sand is gone. We're only left with these coarse-grained particles. So what's the difference? What changes this beach? Why is there more sediment here, fine-grained sediment here, than here during the summer than the winter? Well, what causes this annual progression of beach sand? So here's a cross-section of a beach. So this is the surface of the sand that goes down onto the water in April, and then in June, the dashed line is the former level of the sand in April. In June, you see we have more sand. In August, we have even more sand, and in September, we have even more sand. You see in December, sand begins to disappear. By February, almost all the sand that was here is eroded away. What causes this cycle? It's storms. During the winter in the Northern Hemisphere, there are more storms, and if there's more storms, there's more wind. There's more wind, there's more waves. More waves, more wave energy, more erosion, less deposition. During the summer, less storms, less wind, less waves, less energy, more sediment deposition, so the amount of sand accumulates at the beach. So now we're going to identify some key features associated with the beach. So one is berms. Berms are the accumulation of sediment that runs parallel to the shore, so parallel to the coastline, and they mark, and these berms, it marks the normal limit of sand deposition by wave action. Okay. So here you can see two berms on this beach, one there and one here. So the berm crest is the peak of the highest berm. It's usually the highest point in the beach and corresponds to the shore limit of wave action during the last high tide. So here is the berm crest. So this is where the water was, right here at this berm at the last high tide. And so sand is slightly piled up right there. And that marks the boundary. It marks the boundary between this part of the beach and that part of the beach, the foreshore and the backshore. The backshore is the region of the beach that extends landward from the berm crest and that is not influenced by the waves. So the sediment transport and deposition in a backshore is by wind, and as wind deposits sand, it creates dunes. And so that's why we have dunes, sand dunes, on the backshore segments of beaches. Over the foreshore region is the region of the beach that extends seaward from the berm crest. This is the active portion of the beach that is actively being washed by the waves and submerged and exposed daily during the tides. Okay, so here we can see this would be the foreshore. It's actively washed by the waves and by the tides on a daily basis. So when we're talking about coastlines, any feature that runs along the shore is known as longshore. And so we talk about two features that run longshore. One is the longshore drift. That is the movement of sand along the coastline. That longshore drift is a result of the longshore current. So what the longshore current is you have water waves moving in at an angle. And those waves move in an angle. The water washes up the beach at an angle, the direction of that the wave is traveling. But then it flows down the beach under gravity alone, so it flows straight down the beach. Next wave hits, and the water washes up at a diagonal, and then the back washes straight down. Next wave hit, and the swash, which is the upwash, is up at an angle, and the backwash is back down. So along the coast, there's this net movement of water along the coast, indicated by this arrow right here. That is the longshore current. And that longshore current moves with it sand. And that movement of sand along the shore is known as the longshore drift. So here we can see these structures known as groins. These are structures that are built extending seaward from the coast that are oriented perpendicular to the coastline. And these groins are intentionally built there to prevent the longshore drift. And so sand is caught by these groins and it piles up on these groins. There are some unwanted consequences of these groins. So as sand builds up on the on the upcurrent side of a groin, on the downcurrent side of the groin, there's no sand being brought down to replace it. So as sand is removed here by a longshore current, no sand moves in to replace it, and so the beach actually, the coastline migrates landward. No problem with these groins. So we're going to look at several features, key features associated with depositional coasts. Those include sand spits, inlets, barrier islands, lagoons, sea islands, tombolos, and deltas. So here's an illustration of a depositional coastline. We're going to look at several of these features. So first we're going to look at a sand spit. If we go back, we see this is a sand spit right here. How a sand spit works is the longshore drift moves sand along the shore, and then we get a part of the coastline where there's a bay where the coastline curves in landward, and this sand gets continued from this coast and dropped right here, and sand gets transported past it and dropped right here, and sand is moving past that and dropped right here, so that it just extends the spit. And so you can tell the direction of the longshore drift because the sand spit points in the direction of the drift. So we can see that the drift is in this direction because that's the direction the sand spit points. Okay, the longshore drift is not in the opposite direction, it's in the direction that the sand spit points. So sand is moving along this coast in this direction. It's piling up over here. Another sand spit, the tip of Cape Cod in Provincetown. See this sand spit right there. So next we're going to look at baymouth bars, and this is whenever a sand spit encloses an entire bay. So you can see this sand spit is almost completely close this entire bay. Okay, and then sometimes what exists in those baymouth bars is a little opening known as an inlet. So we can see a baymouth bar here and the inlet. Now this inlet has hard structures built on both sides. Those are known as jetties, and those structures are built there to prevent the longshore drift from closing this inlet up. So next feature we're going to look at are barrier islands. Barrier islands are long islands that run parallel to a coast. So here we see the coast of Maryland, and we see these barrier islands in yellow. They're called barrier islands because all the wave energy coming from the ocean, it hits these islands, and the actual coastline is protected from all that wave energy. So these islands act as a barrier. That's why they're known as barrier islands. You can see these barrier islands off the coast of Maryland. There are these jetties built here, these hard structures built here to maintain this inlet right here. And so that jetty has influenced the to barrier islands, as you can see by the red outline. The red outline was the outline of basically the coast of the barrier islands in 1849. And the black line is the outline of the islands in 1990. So you can see that this island has begun to migrate back. It has actually been an accumulation of sediment on the upcurrent side of the jetty that's been driven by the longshore drift. But on the downcurrent side of the inlet, or the jetty of the inlet, sand is being moved by the longshore drift, but no sand is coming up here to replace it, and so as a result, this island is migrating landward. You can see the further you get from that downcurrent side of the jetty, the barrier island comes close to its original position. But this is because sand is being moved along this beach and is not being replaced. It is causing the beach to migrate back landward. Barrier islands can be dangerous because they are usually nothing but sediment, so they can be easily washed away in case of large surf or storm surge, and are usually low elevation. And so a large storm, the surf or the storm surge, can usually flood a barrier island with relative ease. And so here we see Ocean City, Maryland, which is very vulnerable because any sort of surge or surf will wash in here and flood it. And here we can see a breach of Hatteras Island in North Carolina. So you can see this piece of road is right there. This road used to go all the way across here, but it was washed out right here and here. So see the telephone was also washed out right here. So barrier islands are very dangerous, and so it's actually ill-advised to sink a lot of investment into development on barrier islands, because a storm will eventually occur and result in damage. And so, for examples like Atlantic City, that suffered a lot of destruction during Hurricane Sandy, it would be a good option to repurpose some of that land where the property is destroyed into maybe a park or a golf course or some land use where if it was flooded, you don't have a significant loss in investment, and also you don't have a lot of people living there depending on those structures for their lives. So the next we're going to look at sea islands and tombolos. So here's a sea island here. And what happens is the wave energy, waves coming in, they crash on the sea island, and therefore the sea island casts a shadow on the coastline behind it where no wave energy hits it. And that allows sediment to accumulate. And as sediment accumulates, it migrates towards the sea island that's providing a shadow, and eventually links up with the sea island, forming the tombolo. So now we're going to talk about river deltas, 3 different types of river deltas and the processes that shape them. First, we have a river-dominated delta, such as the Mississippi River. So you can see how this delta has this fan shape. This is because throughout time, this river migrates back and forth throughout this fan, where the mouth is, opening of the river, migrates back and forth, depositing sediment, creating this fan. Now we have since built levees around the Mississippi, preventing it from meandering back and forth, so it's confined to one fixed path, and so it's been dumping sediment at this one location for quite some time. And that's why it has this bulb of sediment extending out from this more symmetric fan. So if this is allowed to evolve naturally, this fan would grow in size over time as this stream meandered back and forth at this river-dominated delta. So the coastline along this delta is mainly influenced by the sediment deposition by the river. Here we see the delta of the Ganges-Brahmaputra River. This is a tide-dominated delta. So you can see how we have these channels that are running roughly parallel to each other. And these channels are washed into the sediment by water flowing up through the delta with the rising tide, and then back down with the falling tide. So there is this movement of water up and down, these large flood and ebb currents that help shape these channels of this river delta. And then finally, we have a wave-dominated delta. This is the San Francisco River, where the river is depositing sediment, but the delta is taking this distinct shape because of wind blowing, when the waves moving sediment along the coast and shaping the coast itself. So the significant wave energy, which we'd expect along the Pacific coast of the United States, being on the eastern edge of the Pacific Ocean. So biological activity can also shape coastlines as well. Things like barrier reefs and mangrove forests. So barrier reefs, so you can see this reef right here, they are called that because waves from out at sea, they come in and they pass over this barrier reef where the water is very shallow. And that causes the wave to break up. And so the wave is not, it's all broken up, it's not coherent by the time it hits the main coastline. And so there's less erosion at the main coastline because this reef is acting as a barrier to the energy, breaking it up before it can reach the coastline. Or mangrove forests are these marine plants that grow these very intense, long, complicated root structures that grow deep down into the ground to extract fresh groundwater. These root structures are so elaborate that sediment settles, it gets deposited because the roots break up the waves, and so the water can't move the sediment around within the roots, so sediment accumulates within the roots. And over time, if enough sediment accumulates, you form new land, and the mangrove forests can migrate even further seaward. So estuaries are bodies of water along coastlines, usually where fresh water mixes with ocean water. And one way that estuaries can be classified is on their origin, how they formed. So we can have drowned river mouths. So this is like the Chesapeake or Delaware Bay or the Narragansett Bay, where you had a river bed, a river channel, river valley that was flooded with rising sea levels, and you had the fresh water of the river flowing into this larger river valley, and salt water, fresh marine water flowing in. Then you have a fjord. This is a river valley. It's carved wider and deeper by a glacier, in which the fresh water from the river and the marine water from the ocean are mixing. Then you have a bar-built estuary. So this is when a barrier island or a baymouth bar cuts off water that's along the mainland from the rest of the ocean, and it's only through inlets that fresh water flowing from rivers from the land into this body of water known as a lagoon, and marine water from the ocean can mix from marine water entering in through these inlets. Then you have tectonic estuaries, where tectonic plate motion causes subsidence and generates an estuary. So this is like the San Francisco Bay. So this was tectonic activity that created that bay. So it'd be a tectonic estuary. Estuaries can also be influenced by and characterized by how the water mixes, how the two different types of water mix. So remember, freshwater and seawater have a different densities. They don't really like to mix, especially if they're forced together fairly significantly. So the first one we have is the saltwater wedge. This is where we have a large flow rate of fresh water coming out of the river. And because we have a large flow rate of fresh water coming out of the river, it comes in contact with this marine water from the ocean and creates this very stark contrast or boundary between the two. And it creates this wedge of salt water underneath that boundary. Next is a well-mixed estuary. Remember, the flow rate coming out of the river is much slower, so the fresh water is flowing much slower, so that the fresh water coming from the river and the marine water coming from the ocean can mix fairly well because they're not slamming into each other. These two fluids at different densities aren't slamming into each other, creating a stark boundary. Then you have a partially mixed estuary. This is when you have a deeper estuary in the fresh water, which is less dense because the less salinity, it flows more out over top of the marine water, which just flows in from the ocean underneath. Then you have a fjord estuary, where you have, once again, similar, the fresh water flowing over the top while the marine water flowing in into the depth of the fjord. And it's actually really cool. In Norway, in some fjords, fishermen out in the fjord can catch freshwater fish in the shallow water, and then cast their lines deeper and actually catch saltwater fish in the fjord, because of the way the fresh and saltwater mix in that estuary. This is the Chesapeake Bay, which is one of the largest estuaries on the east coast of North America, of the United States. And so here's where the bay opens to the ocean. Here's the coastline. As you can see, these various rivers bringing fresh water into the bay. And so you have fresh water coming in these rivers into the bay, and marine water coming in from the ocean. Your color scale represents the salinity. You can see the salinity is much higher on the eastern side of the bay. And one of the reasons is because we have a lot of rivers on the western side of the bay, so we have a large influx of fresh water on the western side of the bay. But also, the Coriolis effect is at play here, because as this salt water, marine water, moves in, it's moving from south to north. Its path is going to be deflected to the right by the Coriolis effect, and so that marine water is going to hug the right side of this estuary. Where there's fresh water flowing down here, its path is going to be deflected to the right, so it's going to hug this side of the estuary as it flows down. And so that's why the eastern side of the Chesapeake Bay has a higher salinity than the western side, because of the location of rivers on the western side, and because of the north-south orientation of the bay. The Coriolis effect causes the salt water to cling to the eastern coast, and this fresh water to cling to the western coast of the bay or estuary. So the Pacific coast, that's an actively rising margin, so because of the tectonic activity or recent tectonic activity there, so that coast is actively rising. So it's like an active plate margin, or continental margin, where you have more tectonic activity lifting it up, so that you have, in some cases, more steeper topography. Where in the Atlantic coast, it's a passive margin, and so that boundary of the continent has been in place for, well, it's been stable for a little bit longer, and so erosion and deposition has occurred, creating a more gradual sloping topography down to the coastline. The Gulf Coast, it is not a plate boundary, also like the Atlantic coast, and unlike the Pacific coast, but because the Gulf Coast is sheltered in there, there's not a lot of wave energy that goes into the Gulf Coast, so the Gulf Coast has fairly extensive depositional coastlines. And we fight beach erosion using different structures. So we talked about some of these structures, these groins, which are hard structures that we build perpendicular to a coastline that extends seaward. So this prevents the movement of sand due to longshore drift. So sand will accumulate on the upcurrent side of a groin, and sand will be removed from the downcurrent side. We also build seawalls to help prevent beach erosion along coastlines. And we also nourish beaches by importing sand when sand erosion occurs. All three of these techniques are actually employed in Rhode Island at various beaches. So that is it for our lecture on coasts. Thank you very much.